Hello students, and welcome to the 13th week of lecture for POSC 2513 Introduction to Political Science. I am your instructor, Connor Alford, coming at you here from the bowels of my doomsday shelter in Durant, Oklahoma. And I really, genuinely hope that you're all having a wonderful coronacalypse, at least to the best of your ability. As you know, this week we're going to take some time to look at the analysis section of your research proposals or your writing assignments for this class. And when I started recording this lecture, I want you to know I was going to use a traditional PowerPoint presentation. This is probably my fourth or fifth time recording the lecture. Basically, here's the deal. I've decided that the PowerPoint presentation approach to lecture content isn't working for our online format, or at least is inadequate and ill-suited for the purposes that we need to deal with this week. It just isn't working for this particular content. So we're going to do things a little bit differently, but don't panic. All of the same information is going to be covered. There's just not going to be a PowerPoint presentation corresponding to this video. Instead, as you can see, I'm going to run you through the documents that were made available to you in this week's coursework folder. We're going to start by looking at the analysis section guidelines and instructions, because I want to take some time to run through this document in exactly the same manner that we would have were we still able to have our traditional classroom discussions. And when we're done looking at the guidelines and instructions for your analysis section, I'm going to jump over to the 9th chapter of your workbook, which you should have already completed by the time you begin watching this video. And I'm going to assume that everyone has completed the assessment and totally read through that entire workbook for the purposes of this video, but I don't want you to be too concerned about redundancy. Some of the content will probably be a little bit repetitious. That's okay. It'll help you remember. But I'm not just going to read word for word the entire chapter. Instead, what I want to do is I want to walk through the broad topics covered by the chapter. I may read bits and pieces, but I'm also going to add to. I'm going to elaborate on the content of that workbook chapter where I find it to be helpful, necessary, or appropriate. And every once in a while, I'm going to jump to a third document that's not available on Blackboard, but that contains some visual aids that I think will help me to walk you through wrapping your mind around some of the key concepts that you need to comprehend for the purposes of your papers and this class. Okay, so that's the course of action. That's the plan for today's video. Let's start with the analysis section guidelines. And if you want to follow along, as I mentioned before, this is available to you in this week's coursework folder. So, if you recall from prior lecture, we've already discussed your data section, where you tell me where you gathered all of the information you need to test your hypothesis. And we've already talked about your methodology section, where you tell us how you use this data to test your hypothesis. What particular statistical methodology did you employ to see whether or not the data you have observed and gathered is consistent with what you would expect to observe were your hypothesis true? So you've told me where you got your data, and you've told me what tests you're going to run. The analysis section of a paper is where you tell me what results those tests yielded. And if you recall, at the beginning of the semester, we talked about potentially getting together on a particular class day and using SPSS or Stata, some sort of statistical analysis software, to actually run your regressions, your chi-squareds, or whatever methodologies were appropriate to each of your respective hypotheses. Obviously, the coronacalypse precludes us from doing so, and therefore, we're not going to get to run our actual analyses. That's unfortunate, but it also makes things a little bit easier for you. Because what you're going to do at this point in the semester is sit down to work on an analysis section where you pretend that you've actually run a statistical analysis, and you tell me what results this imaginary analysis yielded. Now, as you sit down to describe the results of your hypothetical method or your hypothetical regression, I want you to understand that you are also expected to presume you have found support for your hypothesis. In other words, I want you to pretend that you ran your regression. You ran your chi-squared. You actually ran a statistical test, and the results of that statistical test were consistent with your particular hypothesis. Then you're going to describe what that looks like. In other words, if you run a regression, tell me what sort of regression results would be supportive of your hypothesis. If, on the other hand, you wind up running a chi-squared test, then I want you to tell me what sort of results you would expect in a chi-squared test if it lent support to the positive truth value of your hypothesis. So pretend you ran an analysis. Pretend you got positive results that confirmed your hypothesis, that allowed you to safely reject the null hypothesis, and then describe those hypothetical results. And if that sounds intimidating, well, it's not. It's really quite simple. And if you follow the step-by-step instructions here and you pay attention to the lesson content from this week, you shouldn't have any trouble with the analysis section. As you can see, it's not actually all that involved. It's only got to be about 1 page, consistent with the other chapters of this miniaturized research proposal that you're completing for the class as your writing assignment. And you're going to use the same standard formatting that you've been using throughout the semester. 12-point Times New Roman font with standard 1-inch margins and double space. So a double-spaced single-page paper is not difficult to write, and you already know how to complete the paper in terms of technicalities and formatting, because this is the same set of technicalities and formatting that we've worked with all semester. So for example, use your APSA citation methods and you'll get full credit in terms of citation for this particular project. You ought to be able to do this by now because you've been doing it all semester. So we have already at this point talked about the sort of broad overview of the analysis section provided at the top of the instruction manual here, and you're already familiar with all of the formatting and citation guidelines. So let's jump down to the bottom and let's start talking about the particular expectations. When you sit down to write your analysis section, what I want you to do is I want you to create a bullet point list, and that bullet point list should be 4 items long. The first item that you need to make sure you can check off is number 1. What is your hypothesis? In other words, in your analysis section, one of the first things that you need to do is restate your hypothesis in the past tense. In prior chapters, you have told me in future tense, I hypothesized that XYZ. Well, now you're going to tell me in past tense, I hypothesized at the beginning of this paper, ABC. And then we move on to bullet point item number 2, where you need to tell me what your particular statistical results were. And again, you're going to presume that these are the statistical results that support your hypothesis. So the real test here is whether you, by the end of this week, have enough familiarity with the output of regressions and chi-squared tests, like the ones that you're going to be running, in order to figure out what positive results look like. What p-values would you expect to receive? What would you expect to see in your R-squared if you did a good job, had a solid methodology, and you had very, very, very strong support for your hypothesis? So what statistical results you received in this hypothetical universe where you ran a test as described by your methodology section, and that test put out support for your hypothesis. The third thing that you need to make sure you've talked about inside of your analysis is whether or not these results support your hypothesis and why. Okay, so again, you're going to say, yes, these results are broadly supportive of my hypothesized relationship between the independent and dependent variables of the analysis conducted in this paper, and here is why. Here is how I know that these results are supportive of what I predicted earlier in my research proposal. Finally, we're going to close with the fourth and final bullet point where you begin to discuss the real-world implications of your finding. So, for example, maybe you're doing an analysis on the relationship between, let's say, vehicle inspection requirements and the overall amount of air pollution in a particular state or across different states. And your results indicate that, yes, indeed, more stringent vehicle inspection requirements tend to lead to a less pervasive amount of air pollution. Well, in that case, you need to tell me what we can do with that information in a practical sense, how we can apply it usefully. Maybe what you'll tell me then is, hey, this indicates that a policymaker interested in reducing pollution for his or her state might consider increasing the stringency of vehicle inspection requirements because of, and then restate your blah, blah, blah. You get the point. Now, I do want to briefly note, before we move away from this analysis section set of guidelines and instructions, that in many, if not most, proper research papers, the discussion and the analysis section are separated. That means that normally you would have a separate section, or at least a separate subsection, where you talk about the real-world implications. This would not be included under the heading of analysis. But for your papers, we're not going to do that. That would add a whole extra page of work, and it's not really necessary for the central learning objectives in this course. So we're just going to go ahead and merge them together. And again, you should be able to get all of this in a single page. If you're going substantially over a page, then something's probably gone wrong, or you're overcomplicating the process, and we need to have a discussion because you're just creating more work for yourself. But if you have any questions about this guidelines for the analysis section or the analysis section itself, do remember on Wednesday we will have our weekly Q&A session, during which time you can ask me anything that you need me to answer. So now that we've talked about the analysis section, let's go ahead and close out this document. And we're going to jump over to Workbook Chapter 9, entitled The Analysis Section. And you can follow along on your own computer if you would like to look at your copy of the Workbook Chapter 9, but you're also welcome to simply follow along by reading off of the screen, because as you can see, I've displayed, using my screen capture technology, the actual text and content of that chapter. Now again, we're not going to read this word for word, but remember that this part of the chapter and its corresponding activities is essentially meant to familiarize you with some of the basic methodologies that you can expect to use at some point in your career as a political scientist. And we're going to start with the regression analysis. Now, you remember from your textbook and from prior lecture that regression analysis can take many different forms. In fact, it is so versatile, it is so diverse in its various forms, that we sometimes refer to it as the go-to method for social science, or even the workhorse of the social sciences. This is the most common and the most powerful type of analysis that you can conduct, or that you can expect to conduct at the undergraduate level. And the type of regression in particular discussed by your workbook chapter is the simple linear regression. Like all regressions, the simple linear regression is there to test two things. One, the nature of a relationship between two variables, and two, the strength or magnitude of that relationship. We call it a simple linear regression because we're going to look at exactly two variables. We have one independent or explanatory variable, and we have one dependent or outcome variable. And we're trying to figure out how these two things are related to one another without accounting for any of the potential confounding factors. Now, that should set off an alarm bell somewhere in the back of your head, because you know, and I know, that this kind of bivariate analysis is very, very unreliable. No social scientist worth his or her salt would ever try to get away with publishing a simple bivariate analysis where you only look at two variables and you don't account for any confounding factors. So you're not going to run a simple linear regression. You're going to run a multiple regression. Now, that might be a multiple linear regression or some other kind of regression, but it is going to be a multiple regression. A multiple linear regression is the same thing as a simple linear regression, except that you add in some other explanatory variables. You have 3 or more total variables. You still have only one dependent variable, but now you've got 2 or 3 or 4 or more distinct explanatory variables. And it's worth noting that mathematically speaking, there's no real distinction between your control variables and your independent variables. Mathematically speaking, in a regression analysis, they're all treated the same. The explanatory variable that you call the independent variable is just the one that your theory is primarily interested in focusing on, but mathematically, it's not really meaningfully distinguished between in a regression as compared to your various other explanatory variables, the controls you include. So do keep that somewhere in the back of your mind. You only have one dependent variable, no matter what type of regression you're running, but in a multiple regression, you've got at least 2 explanatory variables, and very probably more. In fact, if you've complied with the minimum expectations and guidelines for your writing assignment in this class, you should have quite a few more control variables that you're going to include, explanatory variables that you're going to include. All right, so we know that the simple linear regression looks at a single set or pair of variables, whereas the multiple linear regression is going to include at least 2 explanatory variables. But what about the linear part of simple linear regression? What does that mean? Well, remember, and we're jumping over to our visual aids, remember that a regression is, at the end of the day, about looking at the relationship between 2 variables. And I want you to understand that the regression is only really appropriate when your 2 variables have real numeric values. In other words, you don't want to use this for categorical or nominal data. you want to use a regression when you're going to be working with actual numeric values. In other words, when you have interval ratio variables that you need to work with, then some form of regression is probably the most appropriate type of test for you to use or run in testing your hypothesis. In this example, I've got the daily takings or earnings of an ice cream bar as an outcome variable on the y-axis, and I've got the daily maximum temperature on the x-axis as my independent variable. And by the way, custom dictates that this is the order in which you present your variables. The dependent variable should be on the y-axis, ranging from top to bottom, whereas the horizontal left to right, or x-axis, is where you're going to gauge the value of your particular independent or explanatory variable. Now, if you look at this chart, what you're going to find is that we've got 9 individual observations. For each day, I have made an entry on this scatter plot based on the total earnings of my ice cream bar, and I've corresponded those earnings to the temperature for that day. So, for example, if we look right here at this first dot, that's one data point, that's one entry. And what we're going to find is that the value here in terms of the dependent variable is somewhere between $500 and $1,500. Let's say that that's about, I don't know, $750 that I earned that day. That's going to place me at this particular point on the y-axis. But now I have to decide where this dot is going to be placed on the x-axis. And again, that's going to be determined by whatever temperature I observe on that day. As you can see, the temperature on this day was somewhere between 10 and 15 degrees Celsius, and therefore I'm going to place the dot between the 10 and the 15 on my x-axis. So by looking at this particular data point, this particular observation, you're going to be able to draw information about how much money my bar earned that day and information about how hot or cold it was on that particular day. Now, you're also going to find that the temperature and the earnings here were both quite low. Maybe my hypothesis is that the higher the temperature rises, the more money I'm going to earn selling ice cream at my ice cream bar. So I'll have higher takings. And I think that if you look at this chart, it seems, subjectively speaking, to be roughly supportive of that prediction. So I've got my two variables, my dependent variable and my independent variable, and it does seem consistent with the hypothesized direct positive relationship, meaning that as my earnings increase, my temperature increases. Or rather, as my temperature increases, my earnings increase. Well, in a regression, you're basically trying to figure out how much of an increase you would expect to see inside each of these data points for the dependent variable per unit increase in the independent variable. So let's jump back to our chapter and let's continue talking a little bit about the nature of regressions. So regressions are going to be probabilistic rather than deterministic. They are not useful for testing sufficient condition hypotheses, for example. So if you have a deterministic hypothesis, you're going to need to reach out to me, and we're going to have to talk about how to test your particular predictions, because a regression's probably not going to work in that particular case. But again, if you've got an interval ratio IV and DV, if you're working with a probabilistic hypothesis, in that case, a regression is going to work just fine for you. And there are even certain types of regression that you can use for an ordinal independent variable and an interval ratio dependent variable, but that's more complicated than we need to get at this point in time. Understand, however, that your regression is considered one of the more powerful tools you can use, because while it doesn't have the capacity to really look at categorical data or to test the validity of a sufficient condition hypothesis, it does allow you to measure both statistical and substantive significance. And you're going to remember from past lecture that statistical significance refers to the probability that you can reject the null hypothesis. A null hypothesis is a hypothesis of no relation. So if I am hypothesizing a relation between my earnings and daily temperature, then the null hypothesis would be that temperature has absolutely no impact on how much money I am making at my ice cream bar. So you can think of statistical significance as a gauge of how certain you can be that there is some relationship between the variables. It doesn't tell you the direction of that relationship. It doesn't tell you whether it is positive or negative. And again, to understand that, let's go ahead and jump back to our visual aids. Remember that in a regression, I want to know how strong a relationship is, I want to know what the nature of that relationship is, and I want to know whether or not there is a relationship. The statistical significance is going to be measured as a p-value. And the p-value, or probability value, is going to be a gauge of how certain I am that there is some relationship between my IV and DV. If your p-value is lower than 0.05, then you can say that there is a statistically significant relationship between these two variables. On the other hand, if it is higher than 0.05, you say that it is not statistically significant, that you have not found evidence against the null, that you have not found support for your hypothesis. Why is it that a number higher than 0.05 is not supportive of your hypothesis? Because remember, in a regression, you're actually testing the null. So higher than a 0.05, a higher p-score is more supportive of the null that you are trying to disprove, that you do not agree with, that you don't expect to hold. In other words, a high p-score indicates that there is no relationship between your IV and your DV. But remember, right now we're only dealing with linear relationships. And a linear relationship is basically a unidirectional relationship in which the nature of the impact of the IV against the DV is fairly consistent. The rate of change caused in the DV by changes in the value of the IV is pretty constant. So looking at this diagram right here, we see an example of a simple linear relationship. As A goes up, so too does B. The further to the right we go, the higher we get. The further to the left we go, the lower we get. Conversely, we could find a negative relationship if we start at the top left and our line projects going down. But it is a straight line. It's not a parabola. It's not a U inverted or right side up. And if it is, we're going to need to modify our relationships. That's not something that the regression, or at least not something that the linear regression, is prepared to deal with. Now, what you're going to find is that this line right here, which is sometimes called y hat because it's indicated by this symbol here, is also sometimes referred to as the best fit line. And basically, this line is a visual depiction of what the perfect relationship, the perfect linear relationship with a constant value would look like between these variables. And you can calculate the line by basically creating a line going across your diagram, your scatter plot, in such a way that the distance between the line and each of your observations is minimized. So, in other words, what you want to do is find a way in which you can draw this line and make sure that the distance between this line and each of the observation is minimized in aggregate. So sum up the distance between each observation and the line going vertically, and then when you've calculated that value, you want to make sure it is low as possible. Okay? And importantly, it's worth noting that if you were to simply add these up raw, the positive distance here, the negative distance here, then what you're going to get is 0. Because the negative and positive distances are going to cancel each other out. So in order to account for that, we're going to square the distance between each of our observed values and our expected values, and then we're going to sum them. Keep that in the back of your mind because it will help you to understand some of these other statistics we're getting ready to talk about. But again, just remember, we're looking right now at statistical significance measured as a p-value for linear relationships. So in a linear regression, the p-value tells you how likely it is that there is some relationship, either positive or negative, from bottom left to top right or from top left to bottom right. But it does not tell you which you have. It doesn't tell you whether that relationship is positive or negative. It just tells you, hey, look, I am so and so certain that there is a relationship. A p-value can range from 0 to 1. It cannot be negative because it's measuring a probability. The probability that there is a relationship or that there is not a relationship. A p-value of 0 means that you are 100% certain that you have a relationship. A p-value of 1 means that you are 100% sure that there is no relationship. You have literally and absolutely proven the null. But keep in mind that when we're talking about social science data, there's a lot of uncertainty. And therefore, if you get a perfect 0 or a perfect 1, you've probably done something wrong. I don't think that I've ever seen anyone come anywhere close to a perfect 1 or a perfect 0 in any published social science study. A perfect 1 or a perfect 0 would be difficult to come by in the hard sciences. And we're not hard scientists, we're social scientists. So our results tend to deal with a great deal more uncertainty than, say, a chemist working in a laboratory environment. By and large, the convention tells us you want a p-value of less than 0.05. And if you've acquired that, you have statistical significance. If it's higher than 0.05, well, then you don't have statistical significance. So if you're running a regression, you need to tell me that you have a p-value of less than 0.05, indicating that yes, indeed, there is a statistically significant relationship between your variables. Why 0.05? Well, it's arbitrary. It's convention. There's no reason why we will prefer 0.05 to 0.06 as the cutoff range. It's just what we do. And we're going to conform with that standard. And if you don't like that standard, well, tough luck. You can complain about it in some other paper. It is arbitrary, we get it, but for our purposes here, just understand, conventionally, arbitrarily, the academic community has agreed 0.05 is a good standard for social science research. It would be laughed at in some other hard sciences, but in social science, it's the best we can get because, again, we're dealing with the real world, not a laboratory experiment, and so we've got a lot more uncertainty. The next thing that you can measure with a regression output is substantive significance, which refers to the magnitude of the relationship if there is one. So if you don't have statistical significance, you don't really need to look at your substantive significance. You know there's not a relationship, and therefore you can't gauge the magnitude of a relationship. But your substantive significance is going to be measured as a coefficient, and that coefficient is a single integer. It's a single value telling you how many units increase or decrease you see in the value of your dV for each unit increase or decrease in the IV. A coefficient of +5, for example, means that increasing your independent variable by 1 will increase your dependent variable by 5. Coefficients are not measuring probabilities, so they can assume a negative value. A negative value indicates an indirect or inverse, a negative relationship. And a positive coefficient of +5, +1, or +2 is going to indicate a positive relationship. So if we jump back to this diagram, for example, what we're going to find when we look at the chart on this page is that this would have a positive sign on its coefficient. This line has a positive slope. It goes from bottom left to top right, indicating, again, a positive relationship. But when you run a regression, this scatter plot is not going to show up. Instead, you're going to get an output, which you can see by looking in your chapter, and which we will analyze momentarily. But the coefficient will have a sign, a plus or a minus, a positive or a negative sign, and a positive sign tells you that the slope goes from bottom left to top right, whereas a negative slope would go from top left to bottom right if you diagrammed it out on a scatter plot. Jumping back to the chapter, we can therefore deduce that the coefficient is a measure of the magnitude of a relationship, whereas the sign on the coefficient is a measure of the direction of a relationship between two variables. So if we scroll down just a little bit, we're going to begin talking about yet another important variable, or rather an important value that will be given to you in the output you receive if you were to use a statistical analysis software like SPSS or Stata to test a hypothesis. And this is going to be the r squared. Without getting too technical, the r squared value is the proportion of the variance in the dependent variable, which can be explained by the explanatory variables that you have included as in your regression. And as with the p-value, the r squared value is going to assume values somewhere between 0 and 1. It cannot be negative because it's a proportion, the proportion of variance. So a 1 tells you that 100% of the variance in the value of the dv is explained by your EVs, whereas a 0 means that you haven't explained any. And again, such extreme values, a perfect 0 or a perfect 1, are red flags. They mean you've done something wrong or you're cheating in some way most of the time. I'm not going to say it's impossible to get such values. Mathematically, it is, at least in theory, possible, but it's highly, highly, highly suspect. It's very unlikely in social sciences. But to understand what I'm talking about when I tell you that the r squared tells you how well your model, how well the explanatory variables in your analysis explain variance in the dependent variable, let's go back to our visual aids on the other document. So we're going to scroll down just a little bit. And what you're going to see here is a chart that will have that same best of fit line, that same y-hat line that we talked about a moment ago. But now what we've also done is we've drawn a dotted line called y bar, and we call the dotted line the y bar because it is traditionally indicated with this symbol over here, which looks like a y with a bar over it. But the y-bar line basically is just a straight line that tells you the mean value of your dependent variable. And in a regression, remember, we're trying to explain variation in the value of the dependent variable. So we've got our 9 observations right here. And what you're going to find is that each of these 9 observations has some distance from the mean and the predicted values. Now, we're going to expect that because, remember, we are predicting some degree of variation in a regression. If there were no variation in the dependent variable, it would not be a variable. It would be a constant. And therefore, what we will discover is that it's not appropriate for a regression. So we expect some degree of variation. We don't want to have all of our actual observed values to be equal to the mean. Otherwise, we're not working with the right type of data. We need a different phenomenon for our purposes in this class. But scrolling down a little bit further, what you can find is that each individual observation is actually going to have a distance from the mean. It's going to have a distance from the expected value. Now, we do expect some degree. We do expect some degree of variation, as we've already established. But in the best of fit line, what we're going to find is that the observation right here at the top on the right-hand side of this diagram is higher than predicted. We predicted that because the temperature here was higher than on most of the other days, we would have a higher than average value attached to our earnings for that day, attached to our dependent variable. The green space right here is the expected variation. But what we're going to find is that the actual aggregate overall amount of variation here is higher than we predicted. And the red space here is the unexpected, the unpredicted variation. And the larger this space, the less well we have predicted the actual outcome. So the closer each observation is to your predicted value, to your predicted relationship, to your predicted line, your best of fit line, the stronger your regression is. And so essentially, the r-squared value is going to give you the sum of the distances between your observed and expected variables after you have squared those values. Why do we square those residual values? And we call them residual values because it's what's residual, what's left after we account for what we predicted. So we've got residual values, and we're going to square them. and we're going to add those together. And that's going to be used to calculate our r-squared. Well, we square them because remember, if we just added the distance between each observation and our predicted value, then the positive and the negative would just cancel each other out. But a negative times a negative is always positive. -2 times -2 is 4. -1 times -1 is 1. So by squaring all of these distances, we are getting rid of the negatives so that we can calculate the sum distance, the sum total number of units separating each observation from the best of fit line. And that distance, that aggregate, is going to be measured as an r-squared value. Now again, when you run your regression, none of that is going to show up. Instead, what you're going to discover is that you will get an output which looks something like this. And there's a lot of information here, but you honestly don't need all of it, and it's honestly not all that complicated. So in this example, in this sample regression output, what we're going to discover is that we are looking at a regression that examines the performance of test takers on the science portion of a standardized examination based on certain other qualities. In the regression output, what we're going to find is that the dependent variable is always listed first. So when we see regress science, that tells us that the dependent variable is science. And in this case, science is short for the performance of that test taker on the science portion of the examination. So our dependent variable is what score a test taker received on the science portion of their exam between, let's say, 0 and 100%. The number of observations is 200. That means that we had 200 independent test takers for whom we gathered data on each of our relevant variables. And we already know that the dependent variables are science score, but what about our independent variables? Well, in this case, we've got math scores, we've got gender, 1 equals female, 0 equals male, we've got the social science score, and we've got the reading score. Now, I'll go ahead and tell you a couple of things. Number one, we've got an all right number of observations. 200 is not great, but it's not abysmal. Remember, the very bare minimum I'll allow for this class is 50 observations, and really you want to get higher than that. But 200 is a sound number of observations. If you have fewer than 50 observations, the regressions math just isn't going to work. And you don't need to understand why at this point. Just keep that in mind. Okay, so we've got a decent amount of observations. But I'm going to go ahead and tell you that there are probably factors other than their math score, their gender, their social science and reading scores that would affect their performance. So there are some factors that are going to influence your performance which aren't being accounted for in this analysis. For example, one thing that might predict how well you do on this test is how much time you spent studying for the science portion. And so what we're going to find is that we have this r-squared value. And again, remember, the r-squared value is going to tell you what percent of the variation in the value of the dependent variable can be explained by looking at the explanatory variables of math, gender, social science, and reading. It's about 48%. And that's not great. It's not abysmal, but okay, we're going to accept that. What is the standard cutoff for a good r-squared? Well, there isn't one. Convention hasn't agreed on that. But for our purposes, let's say that you want at least 0.6. You want at least 60% of the variation to be explained by the model that you have run. And if you're below that, there are some problems. Either way, unless you have a perfect r-squared score, that means that there is some explanatory factor that you haven't accounted for. In this case, I'm willing to bet that one of the unaccounted for explanatory factors is studying time. Maybe another one is your socioeconomic status. Maybe another one is your number of years in traditional educational settings. I don't know. It doesn't really matter, but you get the point. There are some things that aren't accounted for, and those would improve the r-squared if added into the model. They would do a better job of accounting for the total variation between the values of the dependent variable. So now we know what our variables are. But keep in mind here, we've got 4 separate independent variables. That means that we're looking at a simple or a sample regression output for a multiple regression, not a simple regression. A simple regression would only look at science and math or science and gender. But let's go ahead and scroll down just a little bit, and let's look at some of these other values. Over here in this column, where you see the symbol p greater than t, you have your p-value. And what we're going to discover is that there is a perfect 0.0000, so on and so forth, p-value for the relationship between math and science. That means that the math score is 100% likely to have an impact on the science score. And while your performance on the math section is probably a really, really, really big predictor of your performance on the science section, remember, these kind of extreme results might occur in samples, but that's very improbable. It would be great, like if you'd had a totally radically good R-squared and a p-value of 0.00, you probably just won the Nobel Prize. But it's not likely to happen. Okay, so this is an example. You're not going to see a 0.00 in any of your own studies, even if you do go on to run your regressions. I promise you that. But that's what the p-value is going to tell you. If you jump down to the social science score, however, you're going to see that the p-value is 0.424. So what that means is that there is not a statistically significant relationship between your social science score and your science score, your social studies score and your science score, I should say, because 0.424 is not going to be lower than 0.05. So the probability of a relationship between your social studies and your science score is minimal. It's not likely that these are in any significant way related. So then we're going to jump over here, and we've got our coefficients. Well, the math coefficient is 0.389, and so basically what that means is that for every point increase in the math score, you see a 0.38 increase in the science score of a test taker. But you're also going to notice that there's no sign attached to that coefficient, which means it's positive. So that is a positive relationship between the math and the science scores. But gender is different. We've got a negative coefficient. And what that tells us is that increasing the value of this explanatory variable from 0 for male to 1 for female results in a 2-point drop in the science score. Now, it is important to understand that because our independent variable here is nominal, it's categorical, the coefficient is a little bit hard to interpret. But basically just understand that what it's trying to tell us is that, on average, a female test taker is going to get 2 points lower than a male test taker on this particular test. Conversely, what if the values of my female, of my gender variable, were sorted such that 0 equals female and 1 equals male? Well, in that case, what we're going to find is that a negative coefficient would tell us that women do 2 better, that men do 2 worse. As you go from 0 for female to 1 for male, you see a 2-point drop in your science score for the typical case. So the way that you have actually measured your variables and assigned values to your variables or coded your variables is going to affect how you interpret the results of a regression output. But if my hypothesis here was that women would do systematically worse, that men did systematically better than women, and the values were 0 equals male and 1 equals female, then this result would be consistent with that hypothesis. I would have a coefficient of 2, which is quite solid in terms of substantive significance. It's negative, meaning that the direction of the relationship is consistent with what I expected, indicating that women don't do as well as men. And if you come back over to the p-value, what you're going to find is that 0.051 is statistically significant. All right. What about the social studies portion? Well, let's say that I predicted that the higher your social studies score, the higher your science score. Well, as you can see, we don't have statistical significance, so I don't have support for that prediction. And I could come over here and I could look at the coefficient, but because we have no reason to think that there is a relationship, the coefficient here is not very meaningful anymore. The reading score is a different variable. Then you're going to get at the bottom this constant. Ignore that. It's not important for your purposes. It does have some statistical significance in other ways, but it's not something that you have to read when you're going through most political science articles. But here's the thing. As you continue in your literature reviews, you can now skip over the analysis section of many of the articles you read. You can simply go straight to their regression output because it's going to look something like this. And so now you have all the information you need to determine whether they've conducted a good, solid test with a solid R-squared and whether their test is consistent with their hypothesis simply by looking at their chart. That's going to save you a lot of reading. And that's how you use a regression. So when you're writing out your regression results, remember, you're going to say, I've got a statistically significant relationship, meaning your p-value is lower than 0.05. I've got a coefficient with the correct sign. And if your hypothesis involves some degree of comparison, let's say you claim that studying has a bigger impact on your grade than gender, you're going to need to look at the coefficient. If we were to say that math has a bigger impact on your science score than your gender, I would expect math to have a larger coefficient than gender. That's not what we see here. Okay, now we're going to need to begin talking about the chi-squared or cross-tabulation test. And technically, the chi-squared test, or Pearson's chi-squared, is a type of cross-tabulation, but it's essentially the main type of cross-tabulation that we use in these undergraduate level political science research courses. So a cross-tabulation is basically a way that we can analyze the independence of categorical data. And as with a regression, the chi-squared approach is technically meant to test the null hypothesis that the variables are unrelated. And it's going to do this by basically comparing the observed distribution of the data that you have gathered on your observations against the distribution that you would expect to see if the variables were unrelated to one another. So what does that mean? And when would you use a cross-tabulation? Well, you would use a cross-tabulation if you're using nominal data for both your independent and your dependent variables. Remember, nominal data is also called categorical data because you basically create nominal or categorical variables by sorting observations into categories. Male versus female, that's a binary variable. It is a categorical variable with only two possible values. So, for example, let's say that you're in a coin flipping competition with one of your friends. And whoever flips a head the highest number of times wins in the competition. You each flip your coin 100 times. And you get, let's say, 50 tails and 50 heads, whereas they get 96 heads. That's highly suspect. Because if it is equally likely that you would get heads or tails, then you would expect it to be about 50-50. It doesn't have to be exactly 50-50. We can leave some room for sheer chance. Maybe it's 52-48 or even 56-44, but 96-4, that dude's got a weighted coin. Okay, so you're basically going to use a cross-tabulation to see how far the observed value, 96 heads versus 4 tails, is from the expected value of 50 heads versus 50 tails. And the higher that number, that difference between observed and expected values, the more likely it is that your hypothesis is true. So let me give you another example. Let's say that I am interested in determining whether there is a relationship between gender and littering. I think men are more likely to be litterbugs than ladies. And I'm going to separate each of my observations into distinct categories based on those two variables. So first, I'm going to separate my 100 observations into 50 men and 50 women. And then within each of those categories, the male category and the female category, I will further subdivide each individual into one of two categories: litters or does not litter. Note that I'm not going to count the overall amount of litter, because the amount of litter is something you count with an actual numeric value. I'm no longer working with categorical data. All of a sudden, I have an interval ratio variable. You had 13 ounces of litter produced in a particular time frame. That's not going to work here. But if my categories are litters and does not litter, in that case, I'm still gravy. Okay, so if you're going to create two categories, one for each gender, and then you subdivide those into two categories, litter and does not litter, you get a total of 4. You've got men who litter versus men who do not litter versus women who litter versus women who do not litter. And what we would expect to see is an equal distribution if there was no relationship between these two variables. So in that case, we would have 25 men in the littering category and 25 women in the littering category, 25 men in the do not litter category, and 25 women in the do not litter category. And that gives us the total of 50 men and 50 women, 100 observations, and our totals are going to be 50 men and 50 litterers, 50 non-litterers. Approximately half of the litterers are male, and approximately half of the non-litterers are male. Vice versa, half of those who do not litter are female, half of those who do not litter are also female. That's a perfectly equal distribution, and if you were to see this, then you would say it's totally random, yo. There's just no relationship between gender and littering, and maybe that's true, maybe it's not. I don't know. That would be an interesting study, I suppose. But this is what a cross-tabulation table looks like, and this would not lend support to your hypothesis. So if you were to manually, by hand, carry out a cross-tabulation, a simple chi-squared test for two variables, each of which are sorted into distinct categories or measured in the nominal level of measurement, this is what you would have. But if you look at the second table, we're going to find that the numbers here are quite distinct. So this is what you might expect, an unequal distribution, if your hypothesis that men were more likely to be litter bugs than women was true. So in this case, what we're going to see is that 45 of the 50 people who litter are men, and only 5 of the people who do not litter are men. Conversely, only 5 of those who do litter are female, and only 45 and up to 45 of those who do not litter out of the total 50 are female. This seems to indicate that, men are much more likely to litter than are women. Men are much more likely to fall into the littering category than the do not litter category, whereas women are more likely to fall in the not littering category than the litter category. That suggests that maybe there is some relationship between these things. If these are your observations, you've noticed a systematic pattern that's true across multiple cases. So when you draw this out, basically what you're doing is you're gathering values so that you can compare what you expect to see, an equal distribution, to what you have actually seen. In this case, an unequal distribution. And you're going to basically use that to calculate a chi-squared value. The chi-squared value is also sometimes called the Pearson chi-square, and it's measured with a sort of x and then an exponent 2. But basically, it's a gauge telling you how different your actual observed values are from the expected equal distribution. And the greater that distance, the more likely it is that there is actually some relationship. Don't know the direction of the relationship. We know that there's a relationship. And what you're going to discover is that because you're gauging distance, the chi-squared value will always be positive, but it has no upward limit. You can get a chi-squared value of 1, or you can get a chi-squared value of 1,000,000. There's no upward limit, but it will never be negative because distance is not negative. I cannot be -1 mile away from you. That doesn't really make any sense. So your chi-squared value, generally speaking, is something that you're going to want to be positive. And if you somehow come to a negative chi-squared value, you've done something wrong. That doesn't make any sense. I'm not going to get into the technicalities, but if you wind up running a chi-squared cross-tabulation analysis, you, broadly speaking, want to try and get a low chi-squared, but you're also going to get a p-value. And you want to look at the p-value, and you want to read the p-value in more or less the same exact way that you would read the p-value in a regression. But it's going to be called asymmetrical significance, or asim significance. So let's take a look at what that actually looks like. These are the results that you would get from a simple cross-tabulation from a chi-squared if you were to go ahead and examine the relationship between a couple of variables using a statistical analysis software to execute that particular test. And basically, you would look right here. See where this circle is, where I'm indicating the p-value across from Pearson's chi-squared? That's a 0.000. That means that there is 100% chance of some relationship between the distinct variables. Now, we could get into this and we could talk about a whole bunch of ways to complicate this. You can actually include control variables in a chi-squared analysis. And a way to kind of think about what that would yield is by imagining that you're running a separate chi-squared for each individual pair of variables, where you have one explanatory variable paired with the dependent variable. And then you're comparing the results across cases to see whether you still see a difference, accounting for the chi-squared differences that have been observed in the other analyses. Doesn't really matter. Basically, just remember you're looking at categorical data, and you're going to try to measure the p-value. So hopefully this has elucidated the distinct methods that you might use. Again, there are many other types of regression, and the particular test you choose is going to depend on the level of measurement used for your dependent and your independent variable, as well as other questions like, for example, am I even doing a quantitative analysis, or am I doing a qualitative analysis? Qualitative analyses aren't going to use either regressions or the cross-tabulation approach to testing a hypothesis. But we're not getting into qualitative research for our purposes here today. So hopefully, again, this gives you enough information that you can complete your analysis section. And if you have any leftover questions, any residual questions, please feel free to ask me during our question and answer session on Wednesday. See you then. Bye-bye.